At the moment, the advocates of quantum computing are still fascinated by its underlying physical principles. They talk about qubits and spinning electrons as if everyone needed to know about them in order to use this form of computing efficiently. But what do we really need to know? Hi, this is David Allen Greer for the Errant hashtag. Today's episode is entitled The Quantum Imagination. When Don left his job, he didn't quite convince me that he was about to devote his entire retirement to the study of quantum computing. I've become fascinated with the subject, he explained as he packed away his books. But while I didn't doubt his sincerity, I also knew that he was building a new house just a few minutes from the marina where he kept his sailboat. As our conversation drew to a close, he handed me a paper about quantum computing devices and urged me to read it. It's a very simple introduction, he assured me, because it's based on obvious physical principles. Of course, obvious physical principles really aren't that important to any form of computing. Computing is not about physicality. It's about imagination. It dwells in the land of axioms and symbols that hold only the meanings that we assign to them. If computing required us to understand physical principles, well, only physicists would then do computation. When I was taking my first computation lessons as a child, a well-meaning friend of my father's argued that I really needed to understand the electronics of the flip-flop, that basic computing element that can store a single bit of information. I submitted to his lessons, but saw no connection between his circuits and my programs. To me, data was a non-material entity that could represent a spacecraft, a musical note, a wall switch, or even a pair of sandals that could help an explorer flip-flop through vast amounts of information. Don's quantum computing paper was an earnest attempt to provide a physical basis for quantum computing. It argued that quantum computing is based on ideas that aren't commonly found in our daily experience, but could be understood with a sketchy and rapid-fire explanation of quantum mechanics. As I read the quick, incomplete description of electron spin, I concluded that the authors were looking down when they should have been looking up. We've trained two generations of programmers whose technical provenance is seeped in lessons from video games. Those games take place in an imaginary world that's quite different from the world in which we live. Yet gamers are able to apprehend these fictional worlds without lessons in quantum or astrophysics, even though at least a few of these games borrow ideas about how to guide the gamer through an imaginary world from the underlying physics itself. Although we don't need to describe new machines in terms of their underlying physics, we've often found it difficult to avoid physical descriptions. For almost 70 years, physicists have been tightly connected to high-performance computing, a combination that has produced many computing innovations. These physicists have provided at least a small but highly attentive audience for technical descriptions of specialized computers. So, for the one company with a commercial quantum computer, D-Wave, perhaps we can forgive its need to explain the physics behind its machine. In fact, the D-Wave machine isn't a full quantum computer, but rather a rough beast that has much in common with the hybrid digital-analog machines of the 1960s. These machines combined a digital central processor with an analog machine that could quickly solve some form of equations, usually integral, differential, or linear equations. Programmers would do most of their work on the digital processor. They'd then prepare their system of equations with a conventional program, map them onto some kind of a data structure, and then make a request of the analog processor by sending that data structure to the analog machine. The analog processor would then solve the problem, usually very quickly, return a new data structure, which would then need to be interpreted by that main conventional digital processor. Rather than solving a system of integral equations, the D-Wave machine solves an optimization problem. Again, programmers have to create a data structure to describe the problem, make a request to the quantum processor, and interpret the results. To create that data structure, programmers need only to understand the underlying rules of the machine. They don't need to base that understanding on the model of quantum physics any more than I needed to understand a flip-flop to grasp the power of symbolic computation. Any successful form of computing eventually grows away from its physical foundations. It hides physical details and imagines the kind of world we wish to create. We'll know that quantum computing has succeeded when it presents a computational model that sparks the imagination, but bears only the slightest resemblance to the physical model that shares its name. This is David Allen Greer for the Errant hashtag. Take care.